All right. Hi, my name's Meredith. Normally I do portable things to application layer protocols. This is my actually first ever serious hardware project, and also my first physical layer playing with protocols project. All right, so people have been playing with lasers to transmit data for a really long time. That's essentially how fiber optics work. This is an article from an Australian electronics magazine from 1997 talking about doing audio transmission over laser. Basically, in this project, you've got an electric microphone which modulates a laser which is received by a photodiode, and then that signal gets translated to the speaker. So yeah, that's all analog. And if we can transmit analog data, then of course we can transmit digital data, which means we can send packets around. Cool. So I said, well, you know, they're absolutely right that you get an enormous amount of privacy if you're transmitting point to point over optical, especially over a tight beam like a laser, which not only is very difficult to intercept, it's also very targeted. Laser beams don't spread out very far, and especially if you collimate them well, which I'm currently kind of not, but that'll happen later on down the line. All right, so we already have hardware that handles the physical layer of digital optical transmission. You'll find those. You find those pretty much free in any broken DVD player that has an optical audio jack. This is a €2 component that has a ridiculously simple circuit to put together. It's like one inductor, one capacitor, and you're done. So that's the receiving end, and this module can receive at up to 15 megabits per second. So that's easily enough to handle 10 base T. So I decided, all right, well, let's see if we can make 10 base T Ethernet work. So the hackerspace in London makes these boards, nanodes. They're basically an Arduino that speaks Ethernet natively, has an ENC 10 base T chip on it. I'm not currently moving Ethernet packets around for reasons that I'll get to in just a minute. But the idea is read data off of a Cat5, translate it into the format that is necessary to that the optical or the fiber optic receiver needs, and will translate into bits, reconstruct that into an Ethernet frame, and move it on down the cable on the other end. Assuming you can aim it right, which it turns out to be, kind of a bitchy process. Yeah, I'm going to be playing with lenses at some point later on down the line. My initial line of thinking was, well, hey, let's just get a Fresnel lens, right? Because that's essentially a magnifier. If you've ever used one of those sheet magnifiers for maps. Looks like a bunch of concentric circles. That's a Fresnel lens. I looked for small sort of credit card sized ones, but the only ones I found were sort of hacked up into smaller smaller pieces, and that didn't end up working so well. So still on the hunt for decent lenses. But what I've got set up here is the prototype so far. Receiving works, transmitting not so much. I'll explain why that is in a minute. So this Arduino here is the transmitter. It's driving a laser module. And then this nanode over here, which is not actually doing anything with Ethernet data, which is why it's not plugged in, is the receiver. You can't really see it through the through the stand that we hacked together with a Dremel tool and a cassette tape. That was Hans's idea.
Make it good, eh?
It worked. It's not like the most stable, but you know it's good enough for now.
Maybe it's good to get the people closer to the.
Yeah, if people want to come up and take a look, feel free. Yeah. So what this is supposed to be doing is the transmitter, and I'll pop this up on the screen for those who can't see. There's people everywhere. All right. So this
protecting on junk.
All right. So what's supposed to be happening here is we're supposed to be encoding, just iterating through low ASCII characters, padding them with basically a sequence to show the start of the frame, then the character, then yeah. All right. So start frame, character, and then stop frame. This is literally supposed to be just sending one character at a time. So it encodes, so this character encoded into biphase mark encoding looks like that. So you go from a car to a 16-bit int. And then if you also include the start-stop frames, you've basically got 5 ints. So what's biphase mark encoding, you might wonder? Also known as differential Manchester encoding. Yes. Okay, so this is kind of this is kind of scary looking, but it's really not so bad. So the problem with normal the problem with just sending data as high and low signals is you have to have a separate clock keeping track of the rate at which data is coming in. Using differential Manchester encoding combines the clock signal and the data signal so that it's essentially self-clocking. The receiver that I'm using uses this second form where you've got the clock before the data. So essentially, if it shifts during if it shifts during a 2-bit sequence, it's a 1. Then it shifts for the clock. It doesn't shift during that, so it's a 0. It shifts for the clock. It doesn't shift during that 2-bit sequence, so it's a 0. It shifts during this one. It shifts during that one. Those are both 1s, and so on and so forth.
You still need a clock.
No, clock. No.
Not a signal, but to get the timing.
Internal clock, you mean?
Yeah.
Right. Yeah. No. It's on it's self-clocking on the receiving end. Is the point I was getting at. All right. So what's it actually doing? Well, let's get the so we have actual like output going. Unfortunately, you'll notice that it's not, well, part of why it's coming in all zeros right now is because it's not lined up very well. I can try and fiddle with it if you want to see like actual data, but still what's going to come across is going to be a mess. Because unfortunately, so the initial rule that I set for myself when I started this project was I'm going to do this as dirt cheap as I possibly can. You know, when you're dealing with when your most expensive part is €2, I mean, not counting the microcontroller, it kind of makes sense. I mean, high-end fiber optic gear costs thousands of euros. You know, this is the high-end Cisco gear that gets used to drive like undersea cables is ridiculously freaking expensive. And it should be because it can switch. What SONET is like 622 megabits a second, something like that. Yeah. You know, so being able to do, we're actually rate limited on this design by the speed of the Ethernet chip, not so much the optical hardware. But the problem I'm having right now, actually, is that I broke my "let's do this as cheaply as possible" rule and actually dropped dropped about 25 euros on like what I thought a proper laser module would be like heat sunk and everything. Yeah, well, it turns out that the like nice fancy laser module also has a voltage regulation circuit in it that means that it can't switch it can't switch as fast as it needs to. So had I just gotten like a €5 laser pointer and taken it apart and ripped the diode out, I could have built my own power switching circuit and problem solved. So that's going to be the next step: is go find a cheap ass laser pointer and take it apart.
Is it also possible to do this with just infrared LEDs and just put it in light?
Yeah, but you wouldn't want to use infrared because the optical receiver is tuned to 650 nanometers, which is visible red.
Okay.
There may be other parts that do infrared.
I'm not meaning about a laser, but just about light.
Yeah, no, you could totally use a 650 nanometer LED.
You'll get a lot of interference though.
Well, that depends on how you do it. So I've been I'm originally from Houston, Texas, and I'm still in touch with a lot of the folks at the hackerspace there, TexRex. And one of the guys there, Forrest Flanagan, is interested in working on the long-range backhaul side of doing point-to-point optical. So what he wants to do is use like giant, 5-watt red LEDs. See if you can find the hardware to switch 622 megabits a second.
Mm-hmm.
I don't know what the hell kind of processor he's going to use for that. But he wants to mount it on top of the of the grain silo, the abandoned grain silo that he lives like a couple miles from, and then set up one of these, a Herschel reflector telescope, and just capture the visible light.
That could be handy.
Yeah. So we're gonna.
The basic technique is also usable in this kind of situation.
Right. Because it's just a matter of can you switch the light? Can you switch the light on and off that fast? And he's been having a hell of a time. Right, without smearing it, exactly. And he's been having a hell of a time finding parts that'll work for that.
Yeah.
He may have to go for just a higher wattage laser. But that said, I mean, a reflector telescope is probably going to be easier for focusing the damn thing. They've got vacuum forming equipment at TexRex, so he's going to be experimenting with making his own parabolic mirrors.
Nice.
So, yeah, that's about it. This is my spare time hack. I'm sorry it's not cooler.
Yeah, you're getting there. I was thinking if you do it in a visual way without lasers, you can use it indoors, for example.
Mm-hmm.
You put an infrared broadcasting device in your room. You can just broadcast digital data in light forms in a room.
Yeah. Yeah,
and then the interference is lower too.
Yeah, and it'll still reflect off of mirrors. The question is just whether the right kind of receivers are available. I know that with so like green lasers are not really diodes. They don't really make green laser diodes. When you buy a green laser, you're usually getting a high infrared laser that's been pumped through a couple of crystals. It cuts down the wattage significantly, Like I have a 167 milliwatt green laser that I don't think I can legally use in Europe. If I were to take the filters off of it, it would be a 1.5 watt infrared laser.
You can burn something with it.
Oh yeah. Len referred to it as the eyeball boiler.
Especially when it's infrared.
Exactly.
Don't look in laser with remaining eyes.
Exactly.
Hey, talking about the Arduino, if you want to do 10 megabits through the Arduino, is the processor capable of doing it, or is this only being used in this test situation? You want to upgrade to a higher processor later?
I want to upgrade to a higher processor later. Part of why I'm prototyping on the Arduino is that I want to start playing around with Occam Pi. If you go to concurrency.cc, okay, so like way back in the 70s, when people were experimenting a lot with parallel computing, a team in England developed a massively parallel CPU architecture called the transputer. And the language that they developed to run on that was called Occam. And then like x86 really took off and nobody cared about massively parallel processing anymore until like now. So in the meantime, Occam has continued to be developed. They kind of glued the Pi calculus onto it and now it's called Occam Pi. And they've also, and so concurrency.cc has the runs on an AVR version of Occam Pi. And so the Pi calculus is basically the lambda calculus for message passing. So if you're at all into functional programming, this is definitely something worth looking into because you're essentially looking at like interrupt-free actor model message passing. So the one thing I'm a little worried about is is like how many CPU cycles it actually takes to take care of a message. So there might be some slowdown based on that. But what I'm hoping is that not only can this end up being an untappable way of transmitting data back and forth, I'm hoping we can also write it in a language theoretically secure fashion and end up with an unexploitable protocol implementation as well.
Mm-hmm.
So, cross your fingers. Any other questions?
Do you plan to do anything about signal integrity, or do you just let Ethernet take care of that? Because I think Ethernet has checksums in the frame, some FCR checksum.
Yeah, that largely depends on what field testing comes up with. I may end up like needing to come up with sort of a layer between the PHY layer and the data link layer. And if that happens, that's okay. There are lots of error correction. There are lots of error correcting codes out there.
What's the distance you want to make with the laser?
Well, so according to that initial article, this guy was saying that with a parabolic reflector, you can get several kilometers of distance.
Whoa.
I mean, I live in Brussels right now, like really close to the canal, and I'm hoping to be able to get from like one side of the canal to the other. If I can ping across the canal, I'll consider this project a success. Figuring out how to there's going to be some some physical hardware only hacking, like figuring out how to how can I build a box that I can mount this stuff in and like have it be adjustable in small increments. And we're also going to have to worry about environmental interference like rain and fog and stuff like that. Birds. Yeah, what happens if somebody stands in the way?
I was thinking also about your story about the telescope.
Mm-hmm.
What if we take a really big ass laser and we point it to the moon?
Moon bounce.
And on the other side we take a nice telescope which is going to look to the pixel on the moon. So we can moon bouncing. You know moon bouncing?
Oh yes, I do
With
in radio.
waves, not with laser.
Yeah.
They do it with lasers as well. There are
Yeah,
mirrors
there's
on
some
the
corner
moon.
mirrors, but that's going to come right back at you. You're not going to go anywhere with it.
Right.
It could be a nice extension of
But you know, if you can see where the laser is hitting the moon, and can focus
That's
in on
one
that.
hell of a laser. You're scorching rocks on the moon.
Well, I mean, this was just a suggestion. I actually don't know how much of how badass it is.
Well, we have a 100 watt laser, and if an airplane comes in between, it lost its wing.
You could project a movie on the moon.
Time delay.
Maybe you should put the camera down.
How many kilometers is it from there to there? Like by 300,000.
Enough.
Whereas in
10 times geosynchronous orbit, I know that one, but I can't tell you.
Okay. Yeah, I don't know that one off the top of my head either.
And it's pretty hard because the atmosphere has got a light deflection. So it would actually, your light will scatter while it's going out of the atmosphere.
Good point. And you know, also, and yeah, that sort of raises another issue too, which is that you know once you're shooting more than about 10 to 15 kilometers, the curvature of the Earth starts to become an issue.
It's just a reason to like have some satellites with lasers.
Why not?
Satellites.
Firing my lasers.
Yeah, but I mean, you know, people already with telescopes, people already do automatic tracking of objects moving in the sky. Like I've gone to you know, astronomy events where somebody points a telescope at Saturn and then has software driving a couple of servos that move the telescope at very tiny increments to track the
A clock year.
Right. And you know, for micro adjustment, I think something like that's probably going to be necessary for this as well.
You're doing.
I'm chucking satellites that way.
Oh, awesome.
You're using the base of a telescope?
No, I'm using the base of antenna assembly.
Yeah.
Oh, sweet.
Yeah. Off two servos up.
Yeah.
Yeah.
Well, actually, it's a DC and an AC motor, which are connected to 2 pop meters,
Okay.
which are used to know where the assembly is.
Mhm.
The whole station is run on, I think, about 250 rows of Python code.
Oh, sweet.
Well, that's excluding the code which does the prediction of the satellites itself, but
Right. Yeah.
that's
Summarize.
going to be rewritten because it leaks memory like hell. You can't have everything first try.
So you're pulling public ephemeris data and using that to.
I'm using the standard Kepler sets which are available for all the satellites in
it's
orbit.
Ephemeris, yeah.
Yeah.
Okay.
Cool.
Using that to predict the azimuth and elevation of all the things I want to track.
I'd love to see that code when you're ready to have like.
Well, it's already online.
Oh,
I can give
alright.
you the link, so no problem.
Thank you. All right.
Any more questions?
Hoe is de lasers?
Oh, yeah, the laser. Yeah, lasers. All right, cool.
Meredith.
Laser's fun.